Hello, I'm Michael Ford, I'm the Group 3 leader, where we will be looking at the Aeron experiment also. It's like just an overview of the presentation. We run into like the objectives of the experiment and all the background behind it, what really we'll be looking at, along with the experiment and what we expect from it. The objective of the experiment is to understand the purpose of the Clapeyron equation, and then to take this and determine latent heat of vaporization of water, and then we'll take that and verify these with the steam tables. So this is the Clapeyron equation we'll be using for the experiment. What it really does is it takes, we're looking for properties that we can't measure. And so it takes the value that we can measure. In this case, it would be the saturated pressure and temperature for water, and we'll use this to find the latent heat of vaporization. So, next slide. To do that, first we have to understand the pressure versus temperature of saturated water. As temperature increases, we can see that pressure will start to exponentially increase as on the hotter it gets. Next slide. The thermodynamic relationship behind this and how to actually realize where our equation comes from, we look at the Carnot cycle and how the reversible steady state processes that happen between like 1 and 2 and 4 and 3, all that. So if you go to the next slide, we can start off with the heat transfer for the high temperatures and the low temperatures. And then we can find the network by taking the difference between these. And we get the next. One of the big things about this equation is that there's no work done between 1, 2, and 4, and 3. This is because there's no pressure difference, and this equation they derive becomes more accurate as we have smaller delta P values. So next slide. When we take the two equations that we looked at with temperature and delta P, and we take the limit as delta T approaches 0, we get our difference in saturated pressure and temperature, and we get the relationships between the two for inside the vapor dome. So since temperature and pressure is constant between 1 and 2, we end up being able to substitute in this FU value and get more closely to the equation we'll be using. Next slide. So then taking ideal gas law, we can substitute in for that specific volume and get rid of it. And we'll have the actual equation we'll be using from the experiment. And this derivation comes from our thermo textbook. So if you're wondering where that came from, you want to look into it more. That's where. Next slide. So our apparatus has 10 components. Summing it all together, we'll have a flask that will be heated by a hot plate. This will be read by a thermocouple sensor, where it will be transmitted to a computer. And we have air valves and a vacuum valve. You get the next slide, along with our other equipment to make sure that the flow stays going for the experiment. So go to the next slide. The experience procedure is divided into 4 phases: the data acquisition system, setup preparation, the actual procedure of the experiment, and our shutdown. So the data acquisition system, I'm going to sum up all the experiment procedures. We have our manuals, but really with here, we're verifying that we set up everything properly. We want to make sure that this is all done correctly. We have the proper configurations by measuring our ambient conditions and seeing what our data is there. Next slide. So for the setup, our instructor will specify the use of boiling beads. This is because we want to see, we want to make sure the heat is evenly dispersed and that we can create bubbles in the boiling so that you don't have any accidents or discrepancies in the data. Another thing to highlight about this is where we place the thermocouple tip is very important. As we learned last week, that you touch the edges of the flask or the beads, they can mess with your data. So you want to keep it just in the water with no interference. And lastly, we want to leak test the system to make sure that there are no leaks and that will cause any discrepancies. So for the experiment, our goal kind of is to, first we want to bring the water to boiling at 0 pressure. And so we'll do that, and by first, you gotta double check the thermocouple. It was highlighted in the manual a bunch, make sure that's right. Then once the water begins to boil, you start logging your data, and you'll close the line of the vacuum pump, but you gotta know that if you do this too fast, you'll ruin the whole experiment because your boiling will stop and you'll have to restart. Next. And so once it reaches a rolling boil at atmospheric pressure, you'll stop recording your data and know this is a calibration check. You can correct the values later if necessary, but after all this is done, you'll be done with the experiment. You can turn everything off, which leads to our shutdown, where, next slide, it's just taking apart the equipment, make sure everything's off, and then you say where your data still be recorded. Next. So sample calculations, took that PVT relationship, plotted the best curve fit, and then took the derivative of that to find our slope, because we need that to calculate our latent heat vaporization. And then rearranging the equations, you can find your enthalpy value, where for this example, if you go to the next slide, 15 degrees Celsius, it says negative 6,000 for that equation. That's definitely not right. This can probably be due to the fact it's when the curve fits, the slope at the PVT is so small at the beginning compared to the rest that it doesn't really know what to do. I think Excel kind of doesn't know what to do, and you're doing a best curve fit. But we can see as we increase the temperature, the pressure becomes more accurate to what it is in steam tables, and our calculated enthalpies start to follow the actual trend that they're supposed to, where they decrease as it goes. But they're still off, and this could be due to, my guess, is the best curve fit of Excel. Next slide. So our expected results will follow the standard relationship of our PVT, and that the latent heat of vaporization should decrease as temperature rises. And there may be uncertainty due to, like mentioned before, the tip, human error, instrumentation error, also how we treat those opening and closing of valves. So that's it. Any questions?